In section 1 of chapter 4, we're going to be going over a concept that is attached to a lot of ideas we've done in the past and a lot of ideas we're going to do going forward. I'm doing this at the very beginning because it's going to help you. This is going to be a tool that is always going to be in your back pocket. You can always pull it out and use it, but you never technically have to. It's something to give you a little guidance. So what we're going to be doing today is utilizing something called the discriminant to identify the total number and type of solutions for a quadratic function. So if you ever looked at a quadratic graph, one thing that makes us curious as mathematicians is trying to find certain characteristics about it. The primary characteristic we're going to be focusing on in this chapter, technically we did it last chapter, is what we are trying to find is where does a quadratic hit the x-axis. That's going to be our primary focus in this chapter, and is going to be the primary focus of a lot of topics moving forward. Is how do I find where a quadratic or other types of functions intersect the x-axis? There's a problem with doing that. One thing that all x-intercepts have in common, however, and this is kind of our guiding principle, our guiding direction, is no matter where you are on the x-axis, the y value is always, always, always going to be 0. But there's a problem in a lot of your algebraic skills and abilities if I just set y equal to 0 and try and solve. There's going to be a formula that is called the discriminant. It's an equation. For right now, it's going to appear like I just pulled it out of my back pocket, I pulled it out of the ether, and it just exists because I say it exists. I, as a math teacher, will it into existence. That is not true. It's just really weird because where this formula comes from requires a difficult technique that we are going to learn. I'm going to show you where this comes from, but it's weird because by the time we get to the part where this does have a good origin story, it's already kind of been overpowered and overshadowed by all the other techniques you have. It's really useful after it's really useful before you learn where it comes from. So I'm just going to show it to you. I will show you where it comes from in this chapter later. So here's the formula for the discriminant. The discriminant is really, 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 really super important and powerful because it can do a bunch of stuff. It can tell you how many solutions there are. It can tell you what kind of solutions there are. And lastly, and this is probably going to be most useful for you, if you're dealing with a quadratic, it'll actually even tell you if it's factorable or not. So all those problems in the past chapter where you're like, I don't know if this is factorable or not, you plug it into the discriminant, it will tell you, yes, you can factor, no, you cannot. All right, so how do we get it? Well, if you're given a quadratic in the form ax squared plus bx plus c, where a, b, and c are just numbers that you can count, the formula for the discriminant is x is equal to b squared minus 4 times a times c. That formula will help us discriminate as to whether or not we're going to have certain types of solutions, how many solutions, and if the original problem is factorable or not. When you plug the numbers, the values into that formula, you're going to get an output that is also a number. They will fall into 3 categories. Each category tells you something different. The first category is if the discriminant is less than 0, meaning it's a negative number. If you plug those values into the discriminant and you get an output of negative 13, negative 6, negative 4.5, doesn't matter what it is. If it's a negative number, then we immediately know that there's going to be 2 imaginary solutions. We'll get into imaginary solutions again later, but for right now what that means is if you were to graph, that quadratic, this is going to tell you where or how many times it hits the x-axis. This would be a quadratic that doesn't. It hits at imaginary locations. It's a little more complicated than that, but for right now that'll do. So if you find the discriminant and it's negative, you're actually getting a parabola that doesn't hit the x-axis, because there are no real solutions. There's two imaginary solutions. Next, if the discriminant is equal to 0, then there's going to be one real solution. That, if you graphed it, would be a quadratic that hits the x-axis at exactly one location. It basically hits the x-axis and bounces off. So if the discriminant is equal to 0, which is really rare, but it does happen, then if you graph that quadratic, it's going to hit the x-axis at exactly one location. And then lastly, if the discriminant is greater than 0, basically if it's a positive number, then that means there's going to be two real solutions. That means if you looked at it on a graph, it doesn't tell you where they're going to intersect on the x-axis. It just tells you that the graph will intersect the x-axis at two locations. So now I'm going to verify what I just got done saying verbally. I have three problems. I'm going to find the value of their discriminant for problems 1, 2, and 3. And in those boxes, you don't see them right now, but I actually have their graphs. I went on Desmos and graphed those functions, and I'm going to verify it after I get the discriminant. So I'm going to get the discriminant and state what's going to happen. Then I'll show you what does happen on the graph. All right, so the first one I have y equals 3x squared minus 5x plus 4. Remember, the number in front of the x squared, that's our a value. The number in front of the x, that's our b value, including the negative. And the number all by its lonesome with no x next to it, that's our c value. I'm going to plug that into our formula. And that's going to give us x equals the b value squared, so negative 5 quantity squared, minus 4 times the a value times the c value. That's going to be equal to 25 minus 4 times 3 is 12. 12 times 4 is 48. 25 minus 48, last I checked, was negative 23. That is the value of my discriminant. It's negative 23. That matches up with the red box, because I have it color-coded. Because the discriminant is negative, that tells me that therefore, that's what those 3 dots mean, by the way, mathematically. It means I'm about to say a statement that comes from the previous steps. Therefore, there are 2 imaginary solutions. And I want us to state it that way. Another way that people often state it is there are no real solutions. I want us to stick with the vocabulary of there being 2 imaginary solutions. Even though some of you probably don't know what imaginary solutions are, we will get into them, I still want to get used to the idea of we're still stating that there are 2 imaginary solutions. So it hits at 2 imaginary locations. And if I reveal the graph, you'd look and see that parabola doesn't hit the x-axis. The discriminant confirmed that. Problem number 2. This one's different because I don't have a y anymore. I just have 0. It is common to either make it y equals or 0 equals. One of the 2 needs to happen. So my a value is the number in front of the x squared. There's a 1 in front of that x squared. The b value is negative 6, and the c value is positive 9. So it's going to be x equals the b value squared minus 4 times the a value times the c value. That is equal to 36 minus 36, which is equal to 0. My discriminant is equal to 0. According to my 3 rules, if the discriminant is equal to 0, I can say that therefore there is one real solution. So this is a parabola that's going to hit the x-axis at exactly one location. I don't know where that is. I'm not giving you a technique yet to find a location. I'm just giving you a technique to find how many times it's going to occur. And if you graphed it, notice it only intersects the x-axis at one location. All right, problem number 3. Problem number 3 has a little bit of a hiccup. It's not equal to 0, and it's not equal to y. Therefore, before we even start using the discriminant, we need to have one of the two happen. Because there's no y in this equation, I need to be equal to 0. So I am going to subtract the 1 to the other side. That gives me 0 is equal to 2x squared plus 3x minus 1. Now it's set up to where I can use the discriminant because it's equal to 0. So it's going to be x equals the b value, which is 3 squared minus 4 times the a value times the c value. That's going to be 9 plus 8, which is 17. That's the discriminant. The discriminant is positive. Therefore, there will be 2 real solutions. And lo and behold, if I graph the original problem, it would intersect the x-axis at 2 locations. Where those locations are, don't know. There's some crazy decimals, but I know that it's going to hit twice. There are additionally 2 subcategories to one of the previous categories. So I also did say that this determines if it's factorable. If the discriminant is greater than 0, meaning there's going to be 2 real solutions, I can also determine if the problem would be factorable or not. And here's how we do that. If the discriminant, I'm doing the purple one right now, if the discriminant is a perfect square, it's a number you can square root, like 4, 3 times 3 is 9, 4 times 4 is 16, 5 and 5 is 25, 36, 49, 64, 81. Did I skip one? I might have skipped one. If it's a perfect square, not only will there be 2 solutions, but the solutions will be rational, and it means the original problem was factorable. On the other side, if you get the discriminant and it's not a perfect square, so it's something like a 7, a 13, something you can't square root without getting a decimal, then there's still going to be 2 solutions, but they're going to be irrational, and the problem is not factorable. So I got 2 examples. First one, realize h of x is just a fancy way of writing the letter y. The discriminant would be the b value, which is 7 squared minus 4 times the a value times the c value. 7 squared is 49. Negative 4 times negative 15 is positive 60. 60 times 2 is 120. 49 and 120 make a 9, a 6, and a 1. This is the discriminant. It's positive, so there's going to be 2 answers. And I don't know if you know this, 169 is the square of 13. Therefore, there will be 2 rational solutions. Forgot my therefore symbol. And the problem is factorable. Number 5, same thing, except just different numbers. My b value is negative 5, so it'll be negative 5 quantity squared. Minus 4 times my a value times my c value. That's going to be equal to 25 plus 8. 25 plus 8 is 33. 33 is positive, so there's going to be 2 answers. But it's not a perfect square, so they're not going to be rational answers, and the problem's not going to be factorable. So I'd say, therefore, there will be 2 irrational solutions. And the problem isn't factorable. So if I told you to factor the function h, you could factor that because the discriminant's a perfect square. If I told you to factor the function k, you would get frustrated and go through all these variety of numbers, ultimately to end up with the statement, I can't factor this, Mr. Sultan.